The mean value. We're going to start by looking at Rolle's theorem. Rolle's theorem says that if you have a function that's continuous on a closed interval and differentiable on its open interval with f of a equal to f of b, then there's at least one point on the open interval where the function has a horizontal tangent line. Now, you've got to have a continuous function. If you don't have a continuous function, then there's no guarantee of a horizontal tangent line. Likewise, if there's any place where the function is not differentiable, if there's a cusp someplace, then again, there's not a guarantee of a horizontal tangent line. Also, the height of the function at a has to be equal to the height of the function at b. So let's look at Rolle's theorem with this function. We're going to find an interval on which Rolle's theorem applies. This function is a polynomial, so it is continuous and differentiable for all values of x. So we need only find an interval where f of a equals f of b. An easy way to do that is just set the function equal to 0. So I set my function equal to 0. It has 3 zeros. I have a few choices of intervals, but if I choose the interval 0 to 5, then that will work. So on the interval 0 to 5, the closed interval 0 to 5, my function is continuous. And it's differentiable on the open interval, and it has the same value at the endpoints. So Rolle's theorem applies. That is, there is some point between 0 and 5 where the graph of f has a horizontal tangent line. And if we want to find those places, well, then we just set f prime equal to 0. So I just find f prime and set it equal to 0. I'm going to have to use the quadratic formula. And when the dust settles, I get 7 plus or minus radical 19, all of that over 3. Notice that both solutions are between my endpoints 0 and 5. And here's a graph of what's going on. So 2 horizontal tangent lines. I'm only guaranteed 1, but I got 2. Now the mean value theorem. And the mean value theorem is proven using Rolle's theorem. Now, the mean value theorem starts off in a very similar fashion, a continuous on the closed interval and differentiable on the open interval. What the mean value theorem does is it guarantees that there's one place on the open interval where the slope of the tangent line is equal to the slope of the line, the secant line that connects the two endpoints. Now, probably even more interesting is that the mean value theorem says that there is at least one place where the instantaneous rate of change is equal to the average rate of change on the interval. One small example. Suppose it takes you 2 hours to drive to a town 100 miles away. While your average speed is 50 miles per hour, you know your instantaneous speed is going to vary. What the mean value theorem says is that at some point during the trip, your instantaneous speed equals that average speed of 50 miles per hour. And it's likely going to equal 50 miles per hour many times, but you're guaranteed at least one. Like Rolle's theorem, the mean value theorem requires continuity on the closed interval and differentiability on the open interval. Can the mean value theorem be used for this function and this interval? Well, no. This function is not defined for x equal to -1, and so the function has a discontinuity on the interval. Can the mean value theorem be used for this function and interval? No. Since f prime is equal to 1 over 2 radical x, this function is not differentiable at 0, which is on my interval. Can the mean value theorem be used for this function and interval? Yes. The derivative we can see that the derivative is not defined at x equals 0. However, I'm only required differentiability on the open interval. It doesn't have to be differentiable at the endpoints. The lapse rate, so we're going to do an example. The lapse rate is the rate at which the temperature decreases in the atmosphere with respect to altitude. The units that we're going to be using are Celsius per kilometer. Now notice that if the temperature is decreasing, then dt dz is negative. And so by putting a sign in front of dt dz, what this does is it just causes the value to be positive. So lapse rate gives magnitude of the rate of change of the temperature with respect to altitude. Now, when the lapse rate rises above 7 Celsius per kilometer in a certain layer of the atmosphere, it indicates favorable conditions for thunderstorm and tornado formation. Now, suppose at 2.9 kilometers the temperature is 7.6, and at 5.6 kilometers, I don't know, maybe there's a balloon taking the temperature. The temperature is now negative 14.3. Assume that the temperature function is continuous and differentiable at all altitudes of interest. What can a meteorologist conclude from this data? Well, with these data points, I see that the average temperature, on average, the temperature is decreasing at a rate of negative 8.1 Celsius per kilometer. So by the mean value theorem, there is at least one altitude where dt dz is equal to negative 8.1 Celsius per kilometer. So let's just think about what just happened. So we don't know what the temperature function is. We only have two data points. And so we found the average rate of change. That is the slope of this blue line. The mean value theorem guarantees at least one point where the slope of the tangent line is equal to the slope of the secant line. So between these two altitudes, there is at least one altitude where the lapse rate is 8.1 Celsius per kilometer, which is greater than 7 Celsius per kilometer. Since the lapse rate rises above 7 Celsius per kilometer for at least one layer of the atmosphere, the conditions are favorable for thunderstorm and tornado formation. And I just want to point out that the data in this problem was recorded in Denver at nearly the same time a tornado struck 50 miles to the north. So you have fun with this section, and I look forward to working with you again. Have a great day.